Okay, we're back for the second video in this sequence. So we have talked about throughout Unit 6 all of the wave nature of light demonstrations and experiments. And remember, Young's double slit experiment is direct evidence of the wave nature of light. Polarizations, demonstration of the wave nature of light, and so on. So we've talked about all of those wave nature terms. Photoelectric effect. This is a direct demonstration of the fact that light exists as photons, which means that light exists as particles. Okay, so basically when we're talking about the photoelectric effect, this is what happens. Okay, and we've used photocells for a long time. Some people have them on top of their roof. Some people use them in their calculator. There are several different ways that we use photoelectric effect. Another method that and a way that we utilize this, opening up a garage door or shutting the garage door. If you step in front of the little laser that goes across the bottom, that laser is photons of light that hits a photocell on the other side. And if you break that particular laser beam, you disrupt the current, so it stops the garage door from closing on you. Okay, so like I said, there's lots of different uses of the photoelectric effect. Okay, so basically what happens? When you shine light on a photocell, electrons are emitted. Okay, and we should know if we get a constant stream of electrons emitted, then we will generate an electric current. Okay, so energy of the photon. Remember, we talked about in the last video, energy is directly proportional to frequency. And remember, frequency, and those of you who have had chemistry, you guys use the new symbol instead of the F for frequency. But energy of a photon is Planck's constant times frequency. Okay? So basically, the photoelectric effect, we'll get into all of this stuff. This is what they knew about it at the time. If they shone the green light on, they would get electrons that were ejected from this photocell, moving at a specific speed. Okay, if they increase the frequency of the light to 400 nanometers, okay, so in the violet region, they would also get electrons that were ejected off of this photocell, but they would be moving a lot faster. But if they put red light onto the photocell, no electrons were ejected. Okay. And basically what happened was and remember, classical theory was based on adding energy over time to be able to get a specific frequency that was emitted. That's what we kind of talked about with the black body radiation. Okay, so what happened here was that no matter how long they put this red light on here and added energy over time to this surface, they could not get any sort of electrons to be able to be ejected. So here's what, and once again, going through this, here's what didn't make sense about these photocells based off of classical wave theory. Okay, so once again, no time lag. Basically, as you add the energy to it, so you shine the red light on it, no matter what happened, they could just sit there and add that on there forever, and they could not get any sort of electrons to be emitted. But even though with the green photons being emitted, with the green light coming in, and getting the electrons emitted, no matter how long they put this green light on, there was no time lag. It was immediately, you shine the green light and the current starts. Okay, so you end up with this velocity maximum, and that did not change. So no time lag. Electrons were immediately emitted. Higher intensity of light increase the number of photoelectrons. So these are called photoelectrons because this is a photocell and we're shining light onto it. Okay, so as the intensity of the light increased, the kinetic energy of these electrons did not change. It was always the same speed of the electrons that were ejected. And remember, kinetic energy is 1/2 mv squared, and we know the mass of an electron. Okay, so based off of the speed that the electrons ejected, we can figure out how much kinetic energy was released here based on that electron. No matter how long they put red light onto the surface, they could not get any electrons to eject from the surface. Okay, so once again, red light, no electrons. And then the energy of the photoelectron, a weak violet light will eject only a few electrons, but their max kinetic energy is greater than those for intense light with longer wavelengths. So basically, we can shine a really intense green light, or we can shine a very just not intense violet light. And the speed of the photoelectrons for the violet light is still going to be greater than the speed of the electrons for the green light. So once again, all those classical theory statements that we used in the last video of how more energy just keeps adding and adding and adding, that wasn't the case here. Okay, so Einstein came in and solved the riddle of this photocell, and this is what Einstein actually won his Nobel Prize for. So Einstein, and I didn't mention this in the last video, but basically Planck was Planck's hypothesis did not go over well. Most people thought it was a complete joke, and they kind of wrote it off. Okay, so it wasn't until several years later when Einstein and Millikan actually verified all of this that Planck was actually given any credit whatsoever. Okay, so Einstein's Nobel Prize. So Einstein basically figured out that light as a frequency can be just thought of as discrete packets, and that's where the term photons come from. So basically, Einstein realized that Planck's quantum hypothesis of the way light behaves was correct. Photons give energy to electrons in the metal and will eject electrons if there's enough energy to do the work. Okay, so basically what that means. We should all know, based off of our intro chemistry classes, that a certain amount of energy is needed to remove electrons. Okay, so if we can overcome that ionization energy, then basically the electrons will be ejected. Okay, so you need enough energy in a single photon to get the single electron to be ejected. Okay, this minimum amount of energy is called the work function. Okay, and the work function is symbolized with a few different things. Some people use just W naught, or it may be, I think it's a psi symbol, I think, if I remember right. It's a circle with the slash line going through it. That's the one I usually use, so just saying. So basically, the energy needed to remove the least strongly held electrons is what's called the work function. So an electron that receives this minimum amount of energy from a photon has zero kinetic energy, and basically is just removed from the atom. Okay, so if we exceed the work function, though, now there's going to be leftover energy. And remember, just like anything else that we talked about with work energy theorem last year, if we have a net amount of energy, we are going to have kinetic energy in the electron now. So if the incoming light has more energy than the energy needed to remove the electron, the rest of that energy goes to the kinetic energy of the photoelectron. Okay, so this is just another example of conservation of energy statement, folks. We've got energy of the photon is going to be equal to the amount of energy needed to remove the photoelectron, okay, which is the work function, plus the kinetic energy. Okay, so it's really, really simple statement. In 1915, Millikan actually ran an experiment and verified that Einstein was correct. So let's spend a few seconds here talking about this graph. So notice this is the maximum photoelectron kinetic energy. Now they have it in electron volts. I'll go over that in a little bit. It's been a long time since we've seen that term, so we're going to have to make sure we go back and understand it. Remember, electron volts is directly, it's just another energy unit. So this is the frequency of light that was placed onto the photocell. So notice as we have these frequencies here, these lower frequencies, which is longer wavelengths. So this is like red light right around in here. Notice that no energy would be, or no electrons would be ejected. On this particular photocell, and I don't know if it says there which type of material he used on it, but basically we get to this frequency of 4.39 to the 14th hertz, which is equal to 683 nanometers. So it's orangish in color. Once we reach this point, notice the graph intersects on the x-axis at 0 right here. Okay, this right here is what's called the cutoff frequency. Okay, because any frequency lower than this will not eject any photoelectrons whatsoever. That particular frequency, if we can use that, so we can take this frequency and we can go, remember, energy of a photon is h times frequency. So if we multiply this by h, which is Planck's constant, we can get the work function, which that gives us, so this is the cutoff frequency, and the work function is the cutoff frequency times Planck's constant, and that is the amount of energy needed to just remove the electron. Okay, now remember, this graph has kinetic energy on the side here on the y-axis. This would also have a negative intercept, negative y-intercept. Okay, that negative y-intercept is the work function. All right, so this times this number times Planck's constant is the negative y-intercept here. And I'll show you when I do a practice problem on this later in the next video. I'll show you where all that's coming from. All right, as we get higher frequency light, now we've exceeded the work function, we've exceeded the cutoff frequency, so now we have energy left over. So what happens is, as we get to 8 to the 14th hertz, now we have kinetic energy in the photoelectrons, okay? So what happens is, and notice this is just a straight line graph, the more and more energy you add in the terms of the photons of light, then the greater the kinetic energy of the photoelectrons are going to be. Okay? All right. Next. Depending on the surface type, every photocell material has a different cutoff frequency. Okay, so this particular material here has a cutoff frequency of 4.39 to the 14th. Another material might have a higher frequency, that is your cutoff frequency. So all that does is shift this graph to the right. The slope of the line, as I will show you in the next video, the slope of this graph is Planck's constant. Okay, so if we have a different material as our photocell, it may shift the graph to the right or the left, but the slope will always be Planck's constant. All right, now, obviously, we're talking about single photons and single electrons here. Energies are going to be really, really small. So a lot of times it doesn't make sense to write the energy in joules. And instead, we want to write the energy in terms of electron volts, okay? So remember, all this is saying is that for 1 electron at 1 volt, there is 1.6 to the negative 19 joules, okay? Because this would be 1 volt. Electron charge, remember, is 1.6 to the negative 19th. So this is your equivalent energy here. Make sure that you remember this and understand it, because we're going to be using electron volts and joules. We'll be working back and forth from these. Okay, so here's basically, we'll see this in a simulation coming up. This is basically how they measured this. Remember I said before, one of the uses of this is to stop your garage door from closing. So basically you got a laser that shoots the photons, and then you got a photocell, and those photons hit that photocell and eject the electrons, creating a constant stream of electrons that are coming off of that, and that constant stream generates a current. Okay, so basically what they had to do was they had to stop the flow of the electrons. Okay, so when I use the term stopping potential, I don't want you to get anything confused with this. This is simply equal to the maximum kinetic energy of the photoelectrons. So basically, one way we can stop this is, remember, if we have a flow of current going one way, we generate, or a flow of electrons going one way, we generate a current that direction. So one way to stop that current is to repel it. Okay, so we can hook up another power supply going in the opposite direction, and if we have an adjustable power supply, we can adjust the voltage, which is electron volts, and once we get the perfect voltage established to stop the flow of electrons in the other direction, that voltage is equal to the electron volts. So that is the amount of energy in electron volts. All right. So it's kind of confusing going back and forth between electron volts and joules, but if you have a 1.5 volt battery, that is saying 1.5 electron volts. Okay. So in order to stop the flow, then we need a voltage going in the opposite direction, or generating a current in the opposite direction that basically sums those up to equal 0. All right. And once again, we'll see this in a simulation coming up here in a couple of days. All right. All right, I'm going to end up doing one more video just on a practice problem on this. These problems really aren't very difficult to solve, but this is kind of an important step going forward. Okay, that's it.